This is problem 3.154. In this problem, there's a steel tube with a fluid inside at some hot temperature of 90 degrees, which I'm shading now in blue. And this fluid exchanges heat through a steel tube out through a fin array to air, which is on the outside. And the outer edge of the entire domain is a circular boundary that is insulated. So the first thing we want to do is sketch the equivalent thermal circuit of the system for the heat going from the inside fluid out to the air. And the second thing we want to do is determine the heat rate per unit length going from the hot fluid out to the air. And then in part C, we're going to look at what happens when you change the number of fins or the thickness of the fins given this constraint, n times t is less than 50 millimeters. So part A and B are more of an analysis type problem, and part C is where you start getting into design. So for starters, we're going to look at what is given. Here, we know the thermal conductivity is 20 watts per meter Kelvin. The inside radius, R1, is 13 millimeters or 0.013 meters. R2, which is the outer radius of this inner tube, is 16 millimeters or 0.016 meters. And R3, which is the radius of the entire domain here, is 40 millimeters or 0.04 meters. We also know that the thickness of the fins is 3 millimeters or 0.003 meters. We know that there are 8 fins. We know that the temperature of the inside fluid, 90 degrees C, and the temperature of the outside fluid is 25 degrees C. Outside fluid, of course, being air. So the first thing we want to do is sketch an equivalent thermal circuit, which we don't really need numbers for. It's more of just a pictorial representation. The idea is that part A helps us solve part B. So in part A, we have to recognize that the heat starts off in the inside fluid. So that's going to be our first node, so T infinity I. And as the heat spreads outward to go from the inside fluid to the air, it first has to convect from the inside fluid to the inside of the wall. This will be an internal convection resistor. And then after it makes it to that inside of that inner tube wall, then it has to conduct through the wall. And then as it reaches the outside of that inner tube wall, then the heat is going to go from this outside of the wall to the air through two means, either directly through convection at that surface of the outside wall, or through the fins. So with that, we have to then recognize that this is a fin array, so we're going to use the overall fin array resistance, RTO. And then, of course, this reaches to the air, and the air is at T infinity O. So the values of the three resistances we have here can be found using our resistor equations. So the inside convection resistance is 1 over HI times the inside area, which is just going to be 2 pi times R1 times the thickness in the page, which we're going to call W. Conductive resistance is going to be the natural log of the outside of that inner tube, which is R2, over the inside, which is R1, over 2 pi times K times this depth into the page, W. And then there's the overall array resistance, which is 1 over the overall array efficiency times the external heat transfer coefficient times the total area associated with the fin array. The overall fin array resistance then depends on two parameters, A to O and A sub T. So let's look at those more closely. A to O, we know from the equation in the book, is 1 minus the number of fins times the area for each fin over the total area of the array is 1 minus the efficiency of a single fin. And A sub T is the area associated with the entire fin array. And you can see from the figure that this is equal to the outer surface area of the inner tube that's not covered by fins, plus the area of the fins themselves. So the area of the outer tube that's not covered by fins is going to be the circumference of that circle that represents the outside of the tube, times the width, minus the areas that are covered by fins, which we know is going to be the number of fins times the thickness of the fins, plus the area of the fins themselves, so plus n times the area of the fin, a sub f, where a sub f is equal then to the area on the sides of the fins exposed to the air, which does not include the tips. So that would just be 2 times the length L times W, where L is going to be R3 minus R2. So if you notice the figure, the fins look like they're straight rectangular fins. So in order to get the efficiency, we can go to table 3.5, and in the table we can see sure enough that we have the straight rectangular fins right here, where the area of the fin is given as 2 times W times L sub C. Notice that L sub C is L plus T over 2. This is due to convection at the tip. Since it's not applicable here, we're going to ignore it. So L sub C just equals L. What this means is that the fin efficiency, eta sub f, is going to be the hyperbolic tangent of m times L divided by m times L. Now on the right side of the screen, you can see that m is going to be the square root of 2 times h over k times t. So going back to our diagram here, we can write out our equations. Eta sub f is equal to the hyperbolic tangent of m times L divided by m times L. The length is R3 minus R2, and m is equal to the square root of 2h over kt. We're given that HI is going to be 5,000 watts per square meter Kelvin, and HO is 200 watts per square meter Kelvin. So we can solve for these resistances. The inside convective resistance is 1 over HI times the inside area, which is 2 pi R1 times W, which equals 1 over 5,000 watts per square meter Kelvin times 2 times pi times R sub 1 is 0.013 meters times a unit depth, 1 meter. And putting these numbers in, you get a value of 2.45 times 10 to the minus 3 Kelvin per watt. The conductive resistance is log of R2 divided by R1 over 2 pi k times W, which is the natural log of 0.016 meters over 0.013 meters, divided by 2 times pi times 20 watts per meter Kelvin times 1 meter. This is equal to 1.65 times 10 to the minus 3 Kelvin per watt. Finally, we have our RTO. And in order to solve for our RTO, which is 1 over eta O HO A sub t, we need to first find what eta sub O is. So eta sub O is 1 minus n times AF over A sub t, 1 minus A sub F. So of course we need to find A sub F, A sub t, and eta sub F. Let's start by finding A sub F. So to get eta sub F, we need to find m, which is the square root of 2h over kt. In our case, it'll be HO over kt. So square root of 2 times 200 watts per meter squared Kelvin over 20 watts per meter Kelvin times 0.003 meters. This gives us a value of m of 81.6 inverse meters. L is 0.040 meters minus 0.016 meters, which is 0.024 meters. So combine them together, m times L ends up being 1.96. Therefore, the fin efficiency is a hyperbolic tangent 1.96 over 1.96 is 0.49. The fin area is going to be 2 times L times W. So it's 2 times 0.024 meters times 1 meter will be 0.048 square meters. The total area, which we know is 2 pi r2 times w minus number of fins times the thickness of the fins times w, plus the area of the fin times n, will be 2 pi times 0.016 meters times 1 meter minus 8 fins times the thickness of 0.003 meters times 1 meter plus 8 times 0.048 square meters. You add all these together and you get 0.461 square meters. So what this means is that the overall array efficiency is 1 minus 8 times the area of the fin, so 0.048 square meters, over the total area, which is 0.461 square meters, times 1 minus the efficiency of a single fin, which is 0.49. This ends up being 0.575. Therefore, our overall array resistance is 1 over eta O, which is 0.575, times HO, which is 200 watts per square meter Kelvin, times our total array area, which is 0.461 square meters, and this ends up being 1.89 times 10 to the minus 2 Kelvin per watt. And so finally we have all our three resistances. We can solve then for the total resistance. We have the inside convection, plus what's due to conduction, plus what's due to the fin array. The inside convection resistance is 2.45 times 10 to the minus 3 Kelvin per watt. The conductive resistance is 1.65 times 10 to the minus 3 Kelvin per watt. And our overall array resistance is 1.89 times 10 to the minus 2 Kelvin per watt. So we get a total value here of 2.30 times 10 to the minus 2 Kelvin per watt. So the heat then that flows through 1 meter of pipe is going to be your inside fluid temperature minus your outside fluid temperature all over R total, which is going to be 90 degrees C minus 25 degrees C over 2.30 times 10 to the minus 2 Kelvin per watt. And this ends up giving us a value then of 2,830 watts. And since this is applied over 1 meter of pipe, then we can say that this is 2.83 kilowatts per meter, which we can then write as Q prime. In part C of this problem, we want to do a design of the fin array. We were told that there's a constraint that the number of fins times the thickness of the fin cannot exceed 50 millimeters. So instead of repeating our calculations by hand, we're going to do it in MATLAB and make a plot to allow us to deduce some insight onto whether or not we want to increase the number of fins versus increasing the thickness of the fins. So we're going to start with our standard line. We're going to clear the memory in the screen and then close all open files. And then we're going to write out what's been given. So we know the thermal conductivity is 20. We know the radius of the inside of the inner tube is 0.013. We know the outside of the tube is 0.016. And we know that the entire domain is 0.04. We know the inner fluid temperature is 90 degrees C. And the outer fluid temperature is 25 degrees C. We you know the inner heat transfer coefficient is 5,000. The outer heat transfer coefficient is 200. So what we're first going to do is we're going to write out, we know the number of fins is 8 in the base case. And we know the fin thickness in the base case is 3 millimeters. So let's go ahead and do our calculations for this. First, we're going to calculate our inside convection and our conduction resistances. And they're independent of the number of fins and the fin thickness. The inside convection resistance is going to be 1 divided by HI times 2 times pi times R1 The conductive resistance will be the natural log of R2 divided by R1 divided by 2 times pi times K. So we're now going to calculate the overall array resistance to get the heat flow per unit length for the base case, just to verify our calculations. So first, we're going to calculate M, the square root of 2 times HO divided by K times T. We'll call this the fin parameter. Next, we can get the length of the fin. It's going to be R3 minus R2. Of course, we can put these together under a single parameter called ML. So we'll call this the dimensionless fin length. So the fin efficiency, eta sub f, we'll call it A to F, it's going to be the hyperbolic tangent of ML divided by ML. The area associated with the fin is this 2 times L, knowing that the width W is just a value of 1. Similarly, the total area, we can ignore the values of W, since they're just going to be 1. And this is going to be 2 times pi times R2 minus N times T plus N times AF. Therefore, our overall array efficiency is 1 minus N times AF over AT, we'll put parentheses around all of these, times 1 minus A to F. So we can then calculate out RTO. RTO is 1 divided by A to O times HO times AT. This is the overall array resistance, Kelvin per watt. So we can then calculate our heat flow per unit length. First, calculating the total thermal resistance is R convection I, so R conduction plus RTO. Then the heat flow per unit length is just going to be Ti minus To divided by R total. So we can print this out. If we run it, sure enough, we get the same answer that we got when we did it all by hand. So these MATLAB calculations are verified in that we get the same number as we got when we did all our calculations by hand. However, we can't do all the calculations by varying the number of fins and fin thickness this way. It's just infeasible. It's a lot of work. So instead, we're going to use the function. So at the top of the screen, we're going to name this function and make this the name of your file. And here, The name of this file is problem3_154A. And what we're going to do is take all these calculations and we're going to move them down. Everything past this point here, we're going to move to a subfunction and we're going to return the value of q. So we're going to say q equals calc q, and from this we're going to get the value of q. So everything else below will then be calculated in this subfunction, calc q, fed back into q, which then we can use to vary the values of n and t. So first off, in this calc q function, we want to look at things that depend on n and t. It's evident that our convection I and our conduction do not, so we can actually move these out. So we'll move these out of this subfunction back up to the main function. We can also move up L, since L is independent of n and t. So we'll move that up. But m is dependent on t, so is a sub f then. A sub f is not. We can move that up. AT is, eta O is, RTO is, and then so forth all the way down to the end. We're not going to print out q right here. We can move it up to here. So just to make sure that our functions are working appropriately, we're going to set this up in this manner. Now we have to look at all the variables inside here now, and we have to use these as calls to the function. So if we look, we need an HO, a K, a T, an L, an N, an AF, R2, our convection inside, our conduction, TI and TO. So we'll bring all of these values up to here. And we'll test it by running it again. Sure enough, we still get the same values. So now, in order to vary these things, we need to vary then n and t. We're going to do it in a couple of different ways here. So the first thing we're going to do is we need to recognize that the minimum number for n, of course, is 8, because that's from the problem statement. And the maximum number of fins is that which satisfies the requirement that the number of fins times the thickness of the fins is less than 15 millimeters. So what we're going to do then is we can say this is going to be 15 millimeters, or 0.05 meters, divided by thickness t. Now this may not be a round number, so we're going to use the floor command to reduce this to a round number. So we can set up our array then as follows. It's going to start at n min, it's going to increment by 1 and go up to n max. And then the number of points in the array is just the length of the array. So we're going to do a for loop from I equals 1 to the number of points in the array, and we're going to grab then the value of q. We need to store q into an array as well, so we're going to set up an array in the zeros command, like so, and we're simply going to say the ith index of q array is going to be based on the numbers we have here, along with the ith index of n array. So if we do this, then we can plot then what the variation then of q array is with n array. And here we're going to use blue dots to represent each of these values. We'll label the x-axis as the number of fins, and the y-axis as the heat flow per unit length. And we'll get rid of that term there. So if we run this, you can see that we do get an increase in the heat flow per unit length based on the number of fins. But we also need to look at variation in the fin thickness. which we can do in a similar manner as we did for the variation in number of fins. We know that the minimum fin thickness is 3 millimeters. And just like above, we can set a maximum thickness. In our case here, it's going to be 0.05 divided by the number of fins n. That allows us to meet our constraint. But we also want to set up an array, just like we did above. However, here, instead of knowing the increment of the array, we had an n array, what we need to do here is we know the minimum maximum values, which are not whole numbers like an n array. So we need to use a special function called linspace, which allows us to set then the minimum value of the array, the maximum value of the array, and the number of points inside the array. In our case here, let's extend the number of points to 100 so we have a more refined plot. And then we can resize our Q array for our new number of points. So again, we're going to do for I equals 1 to the number of points. Okay, we just copy this line up here down. So here, we're not going to vary the number of fins. We're going to leave that as n. But our thickness t, we're going to use for each value of I. And then we can plot it. So again, grabbing these three things up here. Now we're going to plot t array. And since our points are close together, we'll make this a line. And instead of number of fins for our x label, now it's fin thickness. Now the problem here we're going to run into is that first it's going to plot the number of fins versus heat flow per unit length, but it's going to immediately be overwritten then by this other one, this other plot, and the fin thickness. So we do get the thickness plot, but this doesn't allow us to do a direct comparison easily with the varying the number of fins. So what we do instead is we're going to do a subplot command to allow us to compare these two plots side by side. So first we set up the figure, and then we use a subplot command. We're going to have two plots side by side, so we're going to say there's one row and two columns, and in the first slot will be the plot where we vary the number of fins, and then in the second slot we're going to vary then the fin thickness. So if we run this, now we can see we get two plots side by side. And we can do a direct comparison between varying the number of fins and the fin thickness. They both increase, but you can see that increasing the number of fins gets you a better result. We're going from about 2,800 watts per meter all the way up to about 4,200 watts per meter when we increase the number of fins. Whereas increasing the fin thickness to the maximum allowable value, we only get up to about 3,100, which tells us what we want to do in our design is we want to minimize the fin thickness just so we can get more fins to that constraint, n times t less than 50 millimeters is met.